Log on, tune in, find out. Another good idea from Cambridge.
And the first talk is given by Florian Méhats from Rennes in France, and he will speak about the moment problem for quantum hydrodynamics.
Thank you very much, Ansgar. And also, I would like to thank the organizers for the invitation. So, this talk will concern some recent progress on rather old, old work, which started in 2004. This new work is done with Olivier Pinault from Lyon 1, from University of Lyon 1, also in France, and it concerns what we call the quantum moment problem. More precisely, it is a quantum minimization problem with density constraint. This will have some very strong links with the talk of Ansgar. But for the moment, just let me write the problem we solved here. So consider, okay, for the moment, I don't care about the framework. In some physical space, I consider a function, a positive function, n of the space, which is non-negative. Well, it will be strictly positive, in fact. And then a Hamiltonian. It will be minus Laplace plus a potential, or minus Laplace. Can we realize this density as the density of a density operator? I recall that in the quantum framework, the object which describes an ensemble of particles is the density operator, which is a self-adjoint positive operator with trace, with bounded trace, and often trace equal to 1. So, can it be realized by a density operator, but under a minimization problem? So, we have a free energy, which is the sum of a density and kinetic energy. Here, for all my talk, there is a temperature behind, but it will be 1. If not, we put temperature here in front of this quantity. And the density here is a Boltzmann density. The entropy, for instance, is the Boltzmann entropy. So I try to minimize this quantity in the space of density operator, which have n as a density. So this is a generalization of the standard moment problem in the classical physics. I will make some link in a few minutes. Just I recall that for a density operator rho, the density has several equivalent definitions. It is rho of xs, where rho is the integral kernel of the density operator. It can be also written under this form if you choose some eigenpairs of the density operators, rho I, phi I, eigenvalues, eigenfunctions. It takes this form. So you can also take this problem as find a rho I, phi I, where phi I is a Hilbert basis of L2, such that this sum is equal for each point x. So the point here is that we try to realize the density at each point x. Okay, so this is the problem we solved in some simplified in one framework. I will explain in detail. Here is the outline of my talk. So in the first part, I will make a link with this quantum drift diffusion problem. What was the motivation of this work, and what was the origin of the question we tried to answer? I will state the results in two parts. There is a part which concerns existence and uniqueness, and in some simplified setting, we try to characterize the rho that minimizes the problem. And then I will come back to QDD, quantum drift diffusion, and and show some rather old now numerical results, which they have 3 or 4 years, but there will be a link with the old what precedes. So first, the motivation was this quantum drift diffusion model. So this is the what maybe Asgard called this non-local quantum drift diffusion model. At the end, I will make some link with the QDD with bomb potential. But for the moment, I will explain in detail a strategy. So the QDD model was in fact, after some first work of Pierre Degon and Christian Ringhofer, concerning quantum hydrodynamics, I discussed with them concerning the possibility to adapt a certain strategy that I will present to a diffusive scaling in order to get a quantum drift diffusion model. So this motivation was a work that we done that was published in 2005, and more or less the idea was to write with cheap assumptions, I would say, to write a diffusion model, a model for particles at a diffusive scale, but which keep their quantum behavior. And so, since it's at a diffusive scale, we take into account collisions. In some sense, the electrons will, particles or electrons, are transported and are subject to a lot of collision with the surroundings at a certain temperature in this modeling, and we do not want to describe the detailed mechanism of collision, which, as you know, is very complicated. We want to in fact mimic what happens in a classical setting. As you know, when you have a macroscopic equation, it can be usually related to a microscopic one, which is Boltzmann, Fokker-Plante, etc. And the main property, qualitative property of the macroscopic model depends on the structure of the collision operator, and more precisely, it will depend on the local equilibria. So you know that the density function, here it will be the density operator, will at each point of the space, or the physical space, be we converge to some local equilibria, and the transport of the parameters of these local equilibria are really the quantities that we describe in this fluid hydrodynamics, diffusive, well, whatever, macroscopic equation. So these are what is at first glance important at the microscopic level are what are the conserved moments, what is the local equilibrium, more or less what is the kernel of the collision operator, and is there some entropy dissipation which will induce this convergence to a macroscopic model. So I will, so this talk concerns this notion of local quantum equilibrium. Just, I already introduced the link, but I recall, I will write the classical case in a certain way, such that we will make the link more clear. So let me recall some very classical things. So I consider a kinetic equation, say linear BGK equation, with the simplest collision kernel. So F will, so this is a relaxation collision operator of F2 fixed Maxwellian with temperature equal to 1 with the same density. So NF is the density of F, just like before. Rho, N rho was the density of rho in a quantum setting. Here in a classical setting, of course, this is the density. And then I put it in a diffusion scaling, so 1 over epsilon, and epsilon in front of the dt. As you know, at the limit epsilon goes to 0, we have, well, formally, but almost always rigorously, it depends on the framework, of course. F converges to is equal to NFM plus some correction for the epsilon, and NF, this is the macroscopic quantity, satisfy the classical drift diffusion equation. So there was a potential, I forgot to say here, and the classical drift diffusion equation, I write it in this way, which is rather unusual, but very simple. So equation of conservation of charge, dt of n plus divergence of current equals to 0. And the current, I write it like the n multiplied by a gradient of the difference between a chemical potential, A, and the potential, the physical potential. And the link between A and n is expressed in some constitutive equation, n equals to exponential of minus A. Why is it drift diffusion? You take the gradient of this, so gradient of, you take the log, so the logarithm, A is minus the logarithm of n. Since A is minus the logarithm of n, the gradient of A, which is here, multiplied by n, is the gradient of n. So n gradient of A is gradient of n. You put it in the divergence, this is a Laplacian operator. So this is really the very standard drift diffusion equation with some diffusion coefficient here, which is depending on the parameters. Okay, some important remarks. In fact, in the real world, you know that you have some Boltzmann operator, even linear, for instance, in semiconductors. But in this case, you also obtain the same equation with coefficient or matrices, which are different, of course. But this is just a guideline to think that this relaxation operator will give us, we expect that it gives us an equation with a good structure, and then you can fit the coefficient. So we'll consider only in the quantum framework some BGK, linear, not linear, but BGK operator. First remark. Second remark, more important here, in fact, the local equilibrium, which is very simple, NFM, so given an F, the density of F multiplied by M, okay, it's a very complicated way to see this function is to see it at the minimizer of a free energy defined in this way with a constraint of density at each point. But this problem can be solved for each x separately. So think that for one x, you consider the minimizer of integral of f log f minus f, so the entropy plus kinetic plus potential energy. You minimize this under one scalar constraint, and you obtain exactly this function. Trust me, it's not difficult to see. And where is the A? A here, in some way, you rewrite here the link between n and some A, and A is a Lagrange multiplier associated to the constraint NF. So you have a constraint for each x of the space, and A is a function of the space. So in the quantum framework, we will do the same. We'll consider this procedure with the free energy that I presented before, and we will obtain this notion of quantum equilibrium. This is and third point. In fact, this procedure of minimizing an entropy will lead to a well-posed system at the macroscopic level in the sense that in a very rough sense, I say it is well-posed because it dissipates some entropy. So this is a consequence of the H theorem. It is well known. So this is at the classical level. So adaptation to the quantum framework was, this is what we have done a few years before. This is exactly the same strategy. We just have to identify what are the quantum equivalent to the quantity and to the equation we have. So the quantum equation at the microscopic level will be the quantum Liouville equation, or if we want to have a kinetic vision, the Wigner equation. This is equivalent, of course. So in the right-hand side, we write a collision operator that we will build by hand, just by identifying towards which function or which operator we want the density matrix, density operator, we want it to converge when collisions are frequent. So we will we'll define these local equilibria, and then we apply a diffusion scaling, epsilon in front of dt, 1 over epsilon in front of the collision operator, and we cross fingers and we try to obtain something. I will come back at the end of my talk to this QDD. Now I'll devise on this local equilibria. So the idea, the original idea of de Guand-Ringhofer was to adapt Levers-Moore's moment method. So it was written, I just presented with the first moment, but it can be adapted to any set of moments. Try to close the system of moments for the Wigner equation by writing that f, that the Wigner function is local equilibria. So it will be a sort of generalization of a Maxwellian, the quantum. It can be called a quantum Maxwellian. Okay, as a minimizer of an entropy functional under moment constraint. And here, just in the framework of diffusive scaling, since we have only one moment, we have to replace entropy by free energy. It's just so think that free energy is just the entropy. We replace the entropy by what we have to replace in a diffusive scaling in a one moment problem. So the specificity of the quantum framework that makes it very complicated for at least for the calculation. The system is described so by the density operator, and the entropy is a function of this operator. So we have to manage function of operators, of course, and there is a non-local dependence between the equilibrium operator and the density. So the argmin operation of before will not be done x for each x separately, but globally. This is the main and it will keep this problem until the end. Okay. So definition of the quantum equilibrium. This is I just recall the problem of the second slide. So I define for each rho, I define the free energy, trace of rho log rho minus rho, plus the energy, the total energy. And in fact, I write it, the problem I want to describe. I want to describe collisions such which dissipate, which make the free energy decay, and which conserve locally the density. And doing this, the simplest local equilibrium we want to devise is defined thanks to a Boltzmann-Gibbs principle. So the generalized Maxwellian associated to some density n. Recall that in this problem n is a function of x, which is considered as given. So this is the minimizer of, if it exists, of this free energy in the set of density operator sigma, such that this is another formulation for the density. So such that the density of sigma is n. This is the weak form of the definition of local density. Think also that density is the integral with respect to p of the Wigner transform of sigma. We have a lot of equivalent formulations. So there is an infinite set of constraints n. Okay, so now I discuss only concentrate on this problem. So on QDD we had several works with Pierre Degon, Ringhofer, also with a student Sami Gallego. We made some numerics, and all of this was rather formal. And then with Olivier Pinault, I considered the simplest initial problem, which was was it possible rigorously for each density, was it possible to define this quantum Maxwellian? So we hope that it will help to understand this QDD problem. At least this problem was rather interesting. Okay, so main result, this is okay, now I will state the result. I put a certain framework. I will have to show some sketch of proofs. So I put a mathematical framework. So omega will be a domain of RD, bounded or not. If it's bounded, I will consider some boundary condition. I will at some point omega will be just the interval 0, 1 with a periodic boundary condition. So, but for the moment it's rather general. And the set of density operator is a subset of the trace class operator, that is I1, J1 in fact, and is given by the set of operator which have a finite trace, which are this is the set of trace class operator, and when A, the operator A, so rho will be positive, the trace is just the standard trace of the operator, and it is a norm. Well, when it's positive, this is exactly the same, the norm J1. And okay, so I said that we are in a subspace of this operator, because we have to consider only operators which have finite energy. So I define the Hamiltonian, which is the Laplace operator. If in an unbounded domain, I will have a confinement operator, a confinement potential, and if I'm in a bounded domain, I can take V equals to 0. The confinement potential or the bounded domain have a very important role here, and this operator has in our problem to have a compact resolvent. We'll just have we will see at one point here, but it's very important at several stages of the procedure. And E will be the energy space. So the space in which I will look for the operator. So the space of density operators which are positive. I forgot to say positive. Non-negative, of course, non-negative. And the trace of H rho is finite. And for reason of self-adjointness, I write it in this way. I think that is the trace of H rho. This is exactly in a classical setting. I'm looking for functions which have finite second moment. So this quantity is exactly the integral of V square F, if F is the Wigner transform. Okay, so the functions are positive, are finite trace, so finite mass and finite energy. And the constraint, okay, the constraint, I take the space H1, and if I have a confinement potential, I had an assumption, of course, on on function. So Q of H is the form domain of H. Think that it will be H1 if I'm in a bounded domain, and so the density n, the data, which is the density n, is such that its square root is in H1. And of course, if I want to have a trace equal to 1 at the end, I choose n such that the integral is equal to 1. And I consider the set of constraints. So A of n is the space of density operator which have n as density, and rho is n. This is always the same notation. I write it in the equivalent way. So the problem will consist in searching a density operator in this A of n, remember of this A of n, which minimize the free energy. Yeah?
But what you wrote below is a bit weaker, because below you write always the weak formulation by multiplying by test function.
It's a weak formulation.
So what you actually mean is this weak formulation, not the pointwise or the strong thing, which is just one line above.
This is exactly what is your
one
question?
line above, you write n rho equal to m, which is a stronger
Yes.
split. So
Okay, I agree. By this I mean this.
okay.
Think that this has to be understood in a weak sense, and not because, of course, it's not realized everywhere. It's in a weak sense. So the framework is this one, and this is just like here to precise. Okay. So the first result is concern the existence and uniqueness. In fact, this problem has a solution in a rather general framework, in multidimensional framework with a confinement potential, with some rather general entropy. I presented the Boltzmann entropy, but we can replace it by a rather general convex function. And it's not the most difficult part of the job. The most difficult part will be to try to characterize to say something on the minimizer. So just I skip this for the moment. The first reason is the free energy functional. This, so trace of beta of rho, more general entropy plus the energy, admits a unique minimizer in my space of constraint. So what are the assumption? There are some assumption on the entropy. It's strictly convex. It vanishes on zero with some sort of decay estimate with decay assumption, which is satisfied for some power functions and also for the Boltzmann entropy. So this theorem is valid for Boltzmann entropy. And the potential is converging to plus infinity and infinity if omega is unbounded, as I said, with some assumption. I will tell a few words about this, and but I will not insist a lot in my talk. And if omega is bounded, just V can be 0 or some L infinity function. So these are the assumptions for the first result. For the second result, so we try to characterize a little bit more this rho. And in fact, I have to simplify a lot of the things. So we work now in dimension 1. I will explain in detail why we have such restriction. So we are in dimension 1 with periodic boundary condition, and we consider the Boltzmann entropy. So it was the initial problem. Now I have to assume that n, that we have to avoid vacuum. So n, the density which is data, is bounded by a certain constant. This assumption is this constant is strictly positive. And then under this set of assumptions, the fact is that there is a Lagrange multiplier A, and rho, the local equilibrium, is exactly the exponential of the energy plus this chemical potential A. So this is a sort of generalization of at a local point, at a local level of global quantum equilibrium. You know that this is a form of thermodynamic quantum equilibria. So the point here is, so this existence of this chemical potential, so this identification of a function of x, A is the function of x, and in fact it's not a function, it's a distribution. At the end it will appear that it's only, well, we cannot characterize it more than as a function as a distribution in a dual space of my energy space. So H1 pair is the H1 function with periodic boundary condition in omega, which is 0, 1. So A is in the space of distribution, and this result is, I insist on the fact, it is optimal. It is optimal. In some sense, if you do not prescribe more regularity of n on n, you will not have more than this. Okay, so this is, but the point is, how can we pass from more regularity on N or more regularity on A? This is completely open for the moment. So we solve this problem in a weak framework in some sense, but which seems to be optimal here, which is optimal here. So A is exactly the generalization in this setting of the previous chemical potential, which was the minus logarithm of N. So in a remember that in a classical setting, A was minus logarithm of N. Okay, so just okay, a few slides on to explain what is behind each proof. So for the first part, in a rather general setting, so existence and uniqueness of the minimizer. The program is the following. We first show that all the functional we consider are well defined on my energy space. So the free energy is finite when rho in the energy space. Here appear the assumption on the potential, on the density, on the entropy. We show that my space on which I want to minimize the entropy, the free energy is not empty, and then I can consider minimizing sequences, and this is a very standard program, the usual program for this topic. Then I consider minimizing sequence. So I prove that this infimum is not minus infinity, and then I consider a sequence which minimizes the free energy at the limit, and we prove some compactness on this sequence. And if we have enough compactness, we can prove that the rho k after extraction of subsequence converge to a minimizer, and then because we have some strict convexity in the problem, the minimizer will be unique. So first step. So in order to define the quantity, we just have the energy is automatically bounded on my space. So in the free energy, I just have to concentrate on the entropy, and the entropy is finite. This is related to some works. There are several works in RD and in bounded domain of Jean Dolbeau and collaborators, Felmer, Loss, Paturel, and other works, where, for instance, for the case of Boltzmann entropy, they prove some logarithmic Sobolev inequalities for system. I just quote one identity which I find very, very nice. And you saw here that here on the left-hand side, you have some given data. On the left, if I reverse, on the right-hand side, you have some given data. So N, remember that if rho is in the A of N, this quantity is N, and the trace of rho is 1, or some given quantity. This is the energy, and this is here the entropy up to minus rho. So this quantity is bounded from below, and this quantity is negative, of course, because rho is of trace 1, so its eigenvalues are between 0 and 1, so this quantity is negative, and this quantity is bounded. So at least for the Boltzmann entropy, it gives some bounds. And for the entropy, you can work also in the same way. I do not detail. So this is just the first step to start. Then, so bound the free energy in my space with constraints. Then, why is this set not empty? It depends on the assumption on n. Recall that I choose the square root of n in a domain form of the Hamiltonian, say in H1 in bounded domains. If square root of n is in this space, the L2 projector on square root of n belongs to the set of density operator. And what is important is that the density associated to this L2 projector is n. So it belongs to, trivially, to A of n. This is a pure state. So we have at least one pure state in the space, but our procedure is in some sense a way to find the state which is the more mixed, the state which minimizes the entropy, the state which is more more mixed with a given density. So the pure state is probably far from being the optimal, but it is in the space. We'll see at that for the Boltzmann entropy, the minimizer is full rank. Okay, I will maybe pass rapidly on the detail. We have to study, okay, so these minimization problems in a framework of trace class operator. So I have to just look, we had just to look in the books, what are the basic theorems of compactness. So there is some, if you have a bounded data in trace class operator, you have after extraction rather rapidly some weak star convergence. So it's written in this way. And if you have an assumption of a bounded second moment, so this quantity with square root of h in each part that I wrote it simply here, the second moment is bounded. I can pass from compact test operator to bounded test operator, and this bounded test operator means that you can take, for instance, 1 or any L infinity function, and then you recover the constraint at the limit, and maybe it's finished up to some very standard arguments. Okay, so I pass very rapidly. This part is not very difficult, and you just have to put one after the other. As soon as you have introduced the right framework, you have to just put the right theorem. And for instance, I quote a very nice book of Barry Simon on trace class operator, where we found a lot of theorems for this kind of job. And uniqueness stems from the convexity of this. So from the strict convexity of beta, so you put strict here. From the strict convexity of beta, you get the strict convexity of the functional rho gives trace of beta of rho. And the other part was linear. So the free energy is strictly convex. A few words concerning the characterization. So this is the second theorem. Now, omega is the interval, 0, 1, with the periodic boundary condition. Beta is the Boltzmann entropy. And the aim, as usual, in order to characterize a minimizer, is to write the Euler-Lagrange equation associated to my problem. The problem is that it will be this procedure will be rather singular here. I will explain why. So the aim is to compute the derivative, the directional derivative of the free energy. This is not so difficult. The problem is the constraint, because you have to get a Lagrange multiplier at the end. But here you are in a framework of non-commutative quantities. And it will. I just explained in a very few arguments where is the difficulty and how we solve it. So difficulty is of course when you want to. Okay, imagine that rho is the minimizer. You perturb it by delta rho, and you have some parameter t, some real parameter t. And so the perturbed operator has to be still self-adjoint, positive, well, non-negative, and has to satisfy the constraint. which can be written in a weak form, such so we have, so the perturbation has to have a vanishing density, of course, and also, of course, you have to be able to differentiate the entropy in this direction. But the derivative of the entropy, which is this quantity formally, but at the end rigorously, is the trace of beta prime. So beta prime is log. So the trace of log of rho delta rho. Remember that this is minus infinity, of course. Big mistake. So beta prime of 0 is minus infinity, so it is singular, and rho is compact. So the set of well, the 0 will be tested a lot of times. So delta of rho cannot be anything. It cannot be a bounded function in order to have a finite quantity here. Okay, so there are, as I wrote, at least 4 points which are very crucial to satisfy, and we could not find any way to construct the constraint in order to satisfy the 4 points. But only 3. It was enough. So the origin of the difficulty is the non-commutativity. For instance, if you just, okay, you think that at the end, this quantity, since here we have a log of rho, if delta rho is more or less proportional to rho, rho multiplied by log of rho is finite, will have a finite trace. So rho log of rho will have a finite trace. So the first idea is to take a rather bounded operator composed by rho, but of course this guy is not self-adjoint, so you symmetrize it, but this one is not positive in general. So you symmetrize in a more clever way, but this guy does not satisfy the constraint. It's not easy to make it satisfy the constraint because, okay, write it and you will see that it's not easy. So finally what we decided is to forget about the constraint in the first step and just penalize it. And finally, it's not, okay, it's not it's not very original, but okay, so in the first step we get rid of the constraint by penalizing the problem. So we introduce a small parameter epsilon, and we consider the global minimizer now of this quantity. So the free energy plus 1 over 2 epsilon, and the difference of the L2 norms of the density of rho minus the given density. So it will be rather easy to have a minimizer for it, and now the job will be to identify it and to pass to the limit as epsilon goes to 0. Okay, so just a last remaining issue, but which is not concerning the derivation of beta. It was easier to regularize a little bit the Boltzmann entropy, so to go to put it towards the negative x, negative rho, and to get some regular function and to pass to the limit. So just to say that at some stage, the initial problem we solved is a minimization problem with 2 small parameters. So the most important one, which is the penalization parameter, and another one which interferes in some regularization of the entropy. So now 2 slides concerning the resolution of the problem. Step 1, okay, we have now this new functional, so regularized entropy and the penalization. It's not difficult to minimize this globally, then to obtain and to differentiate it with no constraint in order to obtain the Euler-Lagrange equation for the minimizer rho epsilon eta. Then forget about eta, we can pass to the limit, and I write Okay, now I concentrate on this equation. The equation we obtain for the limit rho epsilon takes this form. Just think that I took some, I did not insist on it, but I made this choice. So the perturbation is always in some sense proportional to rho. This is to get some well-defined function at the here. Well-defined operator, of course, in a set of traceless operator. And then at the end we obtain this equation. So formally, get rid of this and this. Okay, you divide by square root of rho, and then you take the exponential. So rho will be the exponential of minus h plus a epsilon. Okay, so formally I get the equation, but of course this is not rigorous. Also we have an expression for a epsilon, but of course there is this 1 over epsilon, but for strictly positive epsilon we have this expression for a epsilon. We have something. So this Lagrange multiplier can be at least at this stage touched by hand. Next step. Okay, so we do exactly what I described. We obtain rho equals to exponential minus h plus a epsilon. Of course, we have to divide by this quantity means in fact proving that this operator is invertible. In fact, the crucial point is to prove that its kernel is 0. So the rho epsilon, as I announced, is will be full rank. We also have to prove that the eigenfunction form a basis. I just insist on it. And for this step, which is a very crucial step, we had to come back to the fact that rho epsilon is a minimizer of some functional, and to differentiate differentiate in some direction of the presumed kernel. So at each step, in fact, we have to remind that you have to remind that you're minimizing a problem. Okay, and the last point, just to pass to the limit. Okay, letting epsilon, so the penalization parameter go to 0, and here this is the place where we have the limitation on a, the limitations. This is the step where we'll have this a in a space of distribution. We have an expression on rho epsilon, and we want to pass to the limit in this. So we have to get some. It is not too difficult to prove that rho epsilon will converge to rho, which was identified in the first theorem, to the minimizer of the initial problem. But now we have to pass to the limit in this expression. So to get a limit for a epsilon, and so the first step is to get an estimate for this a epsilon. Of course, we have an expression, but this prevents from any estimate. This expression, there is this 1 over epsilon, where epsilon goes to 0. So there is we use again this equation where we get rid of this square root of rho here. We multiply by the right quantity where phi is a test function. I skipped the detail, but after some computation, we can bound the integral of a multiplied by some phi, where in the right-hand side we have the h1 normal of phi. So this is the reason why a at the end will only be in a h1 prime space. Okay, framework. So I just wanted to arrive here to explain this point. Okay, so now I've proved my theorems. One general in general dimension, the existence and uniqueness, and in one dimension I can characterize the minimizer. So I can characterize the local equilibrium associated to some density. So now I can come back to quantum Drude diffusion and tell you what can we do with this. So in fact, this what I present now was done formally, because formally you can expect the form of the minimizer. We just proved rigorously it here now with Olivier Pinault, but with Pierre Degon and Christian Ringhofer, we had this formal expression. So knowing the form now of this sort of quantum Maxwellian, so m of n is the exponential of minus h plus a with a very non-local link between n and a. So a is such that the so this is an operator. H is a minus Laplace. So this is an operator. You take the density associated to this operator, and you have to this density has to be n. And you can formally derive the QDD model. We did it with the Chapman-Enskog expansion, formal Chapman-Enskog expansion, and finally, after some rather, I would say, lucky commutator vanishing procedure, commutator computation, etc., cancellation. Yeah, thank you. We obtain this form. I write it on purpose under this form. You see that the charge, the conservation of the equation of conservation of mass is the same as in the classical model. The second equation is also the same. So the current is a factor n multiplied by the gradient of a chemical potential. So the A I constructed minus the potential. And what is the difference? You just change a constitutive equation. Instead of F equals to n the Maxwellian, you have n is the density of a rho, which is the local equilibrium. So you just have to deal with this new constitutive equation, which is fully non-local in space. N and A depend each other. Each quantity depend of the other one at each point of the physical space. But okay. But finally, we get this equation. So it's rather interesting to get something rather familiar, for which we are very familiar, except for this. But what is also interesting is that in fact it's possible to deal with this kind of system numerically. It's possible to write some algorithm to compute numerically the solution. I will show a few results, and it was done in a PhD thesis of Sami Gallego that we co-supervised with Pierre Degon. Okay, and a few points before the end. It seems to be there are a few slides for numerical results. It will not be so long. So some formal properties of the QDD model. I think it's interesting to insist on this part. First, well, I said the positivity of the density is guaranteed. Of course, it depends. If you are able to construct rigorously a solution of this, the density, since rho is given by some exponential, the density of such function will be positive. So, okay, I exaggerate a lot by writing this, but I just mean that numerically it's possible to write some algorithm such that it's easy to keep this property. And second, as I said, as a byproduct of the whole procedure, finally, minimization of free energy at the macroscopic level, we still obtain a quantity which decays. This quantity is written in this way, but this is exactly the free energy of the local minimizer. But now it depends on the macroscopic quantity, so minus integral of n multiplied by a. remind that in the classical setting, A is minus log of n. So this is integral of n log n in the classical model, plus integral of nv, and this quantity, at least for a given potential, not depending on time, decays, and there is an expression of the dissipation of entropy, and you can guess that if there is convergence to some equilibrium, A will be adapted and equal at the end to V. So the global equilibria are such that so the system tends to go to when time goes to infinity to A equals to V. So rho will be the global quantum equilibrium. So it's also very, very interesting to see this. And last point, Arsgaard presented a lot of well-known models with a so-called Bohm potential. You recognize this term, which was in Arsgaard's talk. We can make a link between this non-local model and the models that Arsgaard presented. If you put an h bar, the Hamiltonian was minus 1/2 of Laplace, but if you put minus h bar square over 2 Laplace, and you make formally of course some semi-classical expansion, when h bar goes to 0, A becomes minus log of n. So you really recover formally the classical system as a limit of our system when h goes to 0. And we also computed the next order term, which we thought, well, this model seems very complicated. Let us just consider the next approximation after the classical system, and we recover exactly the Bohm potential with a factor 1/3. In fact, the Bohm potential is s bar square over 2, and we divide it by 3, and this was exactly the system. This 1/3 was written by physicists. I don't know how they divided it. They guessed it, but this 1/3 was here for mixed state, to describe mixed state. Here we found this system in a formal calculation, and then you can imagine the h bar 4 term. Arsgaard has done the computation. You said that we done the computation. I think it's you. This term. Well, I don't remember. Maybe or maybe not. Okay. By the way, if I've done it, I will not do it again. So okay. So this were, and just to finish some illustration. So I put a one-dimensional system where we want to have some quantum effect. This is the well-known resonant tunneling diode. So it's a sandwich system where we have some materials here, another one, etc. And then there is the electrons will flow from here to here, and we'll see a double barrier. And there are some quantum effects. The first test case is I put some insulating boundary condition, and then we expect convergence to the equilibrium. And in a second test case, which we want to have to observe an IV curve. IV curve is you make some electron flow from reservoirs from the left to the right. You apply a difference of potential V, and you compute and you wait for an equilibrium current, and you plot the current as a function of the applied potential. And we expect to see negative differential resistance. I just said that in fact it's easy in the system, in the final system, to add the nonlinear effects. and this is what we have done in a computation. So as a function of okay, so k is the iteration, so this is time. Here I plot the potential seen by the electrons, and this curve is the density. So we put so this is the case of the insulating boundary condition at the density here, and the electrons will cross the double barrier, and at the end they will so this is more or less the equilibrium. At the end the density is symmetric. There are very few electrons here, no electrons inside the barriers, and we have an equilibrium. What is interesting is to see the function v minus a. You see at the beginning for the initial data it's nothing, and at the end it's constant more or less, and the free energy is really decaying. So in the case of more realistic boundary conditions, so I apply some you connect the system to some reservoirs, and you apply some voltage, you observe the current, you have this kind of curve. Okay, I don't compare. I think we were at the beginning, so we don't compare with the experimental data. I just want to show that we have some expected quantum effects. Okay, we compared with curves, but this is not the topic here. So I conclude. Just okay, this is what we have done. We have solved in some cases the problem of quantum moments. In fact, it's possible to extend it to the second moment problem. So you prescribe the density and the current. If you want to prescribe also the energy, there is a problem. There will be a problem, a lack of compactness. So for the moment, we don't know how to solve all the moment problems. Okay, a difficulty concerning the characterization in order to extend from one space dimension to several space dimensions because of this h-1 space. And well, the program. Okay, I came back to QDD in this talk, but the game now, the job would be to try to justify quantum Drake diffusion, to construct solution for quantum Drake diffusion, and try to make this as semi-classical asymptotic rigorously, and then go towards more complicated quantum hydro. So for this system, you had the talk of Ansgar and the works of Ansgar with his collaborators, and you have also a poster of Pina Milicic, and I hope and Quantum Navier-Stokes. I hope you will go and look to this poster. So thank you for your attention. Just an announcement concerning Naoufel Ben Abdallah. You probably know, but for those who don't know, there will be a conference organized in memory of Naoufel in Toulouse. Please note the web page of this conference and the date. So it will be in Toulouse, where he was a professor. Thank you very much.
Thank you too. So are there some questions, remarks? Yeah.
Just a question. If you take a pure state, you recover the Bohm term and you have the fourth order diffusion equation of Ansgar. Can you get the sixth order term by some specific ansatz? Not going to the semi-classical expansion.
Yeah, I understand. I don't know.
Taking the two.
I don't know. Completely don't know. But interesting question. Yeah. Yeah, I don't know. Oscar, you try.
I would doubt, but I'm not sure. So since, where this sixth order could come from.
If you combine it with h bar between two, maybe, I don't know. Yeah.
I would have another question concerning more the modeling. Why does it make more sense to start at the kinetic level, say, use a relaxation operator, and then take a diffusion limit, than writing directly the reduced free energy for the constraint and looking for gradient flow. You are building a gradient flow.
Yeah, yeah. This is exactly what we do. Yeah.
So why would it make more sense to do that?
Well, first answer, you recover the same system. At least formally, this is what we're working on this topic with the gens. So I don't know. It's modeling. I don't know. The idea was really okay. To apply to this, well, in fact, the initial idea was written for quantum hydro, so it was not diffusive, but we passed from this to diffusive, and then it was natural to do this macro procedure. But I agree with you. In fact, you just prescribe the free energy, and you get the system with the description. So maybe for when you think on a more complicated system, if you want to put some really more physical inputs from collision kernels, then you will have to do this Chapman-Lenz code. But still, I don't know how to describe. But if you're able to do this, I think you have. Well, when you do the gradient flow, you have no description of collision. You have only free energy.
In a sense, that's what you do.
That's what we do. I completely agree. We are really at this stage. But if you want to put some more physical inputs, it will be easier.
Yeah. Okay. I have several questions. So what I did not fully get is where in the proof did you all of a sudden need to specify to 1D with periodic boundary conditions?
Okay. Periodic is not okay.
Right. Is periodic essential or not? Or
Okay. What is okay? Another. Add a question to yours. Why do I have to specify that n is bounded by a C0? And it will be okay here. When I want to really get some estimate on this, before that, okay, it's rather smooth. But you penalize the system, it's okay. Now you want to get a limit, and okay, maybe we did not find we did not use the good tool, but we tried. Okay, when you want to multiply by this kind of quantity, n doesn't have to vanish. Then, if you want to take some directly boundary condition, the function will vanish at the boundary. So now you will have to specify the way the function will vanish at the boundary. But I would say that the Neumann boundary condition will be okay, completely okay. Other question: 1D, one dimension at many points, and most importantly here, we have to have an algebra. An algebra. The function we want the function n and all the densities to be in L infinity. And as I explained, they are in H1. Okay. So if they are not in L infinity, all the operators of multiplication by the density will not be bounded. So they will not be okay. The trace class operator multiplied by them, I don't know if they are still trace class, etc., etc. So H1, well, dimension 1 is important here at many points, but I just told you some points.
And when you have to pass to this other sort of formulation with this penalized functional, because you said that okay, you can it's not so simple to do this differentiation. I mean, but if you rewrite everything in terms of Schrödinger equations, right? System of Schrödinger equations, shouldn't this tell you what is the right? I mean, there you don't have any problem with non-commutativity, so to say. Shouldn't this be simpler there? Or
well, it's okay. You have a system of Schrödinger equation. You have to perturb it, to perturb the set of function but it has to be still a Hilbert basis. Well, I don't know what is easier. Okay. Okay. At every point, we have to at every point we translate it. Is it easier to describe rho or the phi I? And when you perturb, we try to perturb the first one, and etc. etc. We tried this kind of stuff, but well, finally it's not so okay. At least for this result, it's sufficient to do this. But
Okay. So no further questions. Then let's thank you again.